Ricardo, we cannot hear you. I don't know if you're talking, but...
Oh yeah, sorry, I was muted. Hi everyone, my name is Ricardo, and I'm a master's student at CRCT, and today I'll be presenting some of my research project, which is related with the short-range ordering, glass forming ability, and different aluminum alloys. So I'm going to start with a little bit with the context. Well, my research interests are mainly in undercooling and inoculation. And to study this, I'm using classical molecular simulations. So I'm using LAMP software and
Ricardo, could you speak a little louder or closer to your mic?
yes,
I'm
I
difficulty
guess.
hearing you.
Is it better now or is the same?
A little bit better.
Okay. I
A
can
little
try
louder
to
would be better.
I can try to connect audio with a different source if you want.
Sure.
Oh, that's fine. You can proceed, Ricardo.
Okay. Okay. So I was saying I'm using the LAMP software to perform the simulations, but I'm also using Backstage for validation purposes. So to give a little bit of context, this is an example of a crystallization of pure metal. As you can see in the green line, we start in the liquid, and there's two important elements here, which is undercooling and nucleation, and this is why where my research focus on. So some of the systems of interest during my research are aluminum chromium and the ternaries aluminum copper zirconium and aluminum titanium zirconium. So we first started with aluminum chromium because it was the potential, which is a key ingredient for the simulations, was already reported on literature. But after that, we noticed that by using different potentials, there were some inconsistencies. So we decided to parameterize the next models using the same formalism. And this is why now we are relying into the memes second nearest neighbor. So during my research, I'm also giving a lot of interest to the short-range ordering, mainly to the icosahedral structure. This structure was already proposed by Frank as an explanation for undercooling, and it consists of a center atom, which is surrounded of 12 atoms in the shell. And this is an example for aluminum 12 chromium. So from the first simulations I presented before, we have performed a simulation to understand the stability of the icosahedral cluster. So the first simulation here I'm presenting is just putting the cluster inside of a solid FCC matrix. So it's just a relaxation at 0 Kelvin. And from the results, you can see that for when the cluster consists in just pure aluminum, is less stable than the FCC phase. However, when they add chromium in the center, it becomes more stable and can coexist with the FCC phase. After that, we were able to perform also some simulations in the liquid state to see how it interacts with it. The results are kind of similar. We can see we are at 400 Kelvin, which in undercooling. And we notice again that when we have only pure aluminum, the cluster dissolves into the liquid. However, when we have the presence of chromium in the center, it coexists with the liquid phase. So now we move on to the other system we are studying, which is aluminum copper zirconium. And this is a system of interest because it's important in the 2000 series aluminum alloys. Now we've noticed that the copper concentration is between 2 and 10% in these alloys. And this is important that I'll explain later because of some problems in the parameterization of aluminum copper interactions. Also, copper and zirconium have different grain refinement effect on aluminum. So zirconium is going to be added only in small compositions. So these 2000 series aluminum alloys have a lot of applications, such as bars, fittings, and wires. And here's an example of the design of experiments we are intending to run. So far, we started with aluminum zirconium, and since we're working on the parameterization of copper, we haven't started the second part yet. So during the parameterization of my potential, we noticed that in literature it was already reported for pure zirconium, the HCP potential, and we wondered what would happen if we also added BCC zirconium. So as you can see, when we pass from the liquid to the solid, the first or the primary phase is BCC. So we want to study also the effect of having the potential parameterized into BCC reference and HCP reference. So as I mentioned before, this is a key ingredient for molecular dynamics to account for internal potential energy. So we parameterize these potentials coming from DFT calculations. Then we use the secondary neighbor formalism, and then we proceed to the validation of the potential using elastic constants or enthalpy of mixing. So here, just to show a little bit the effect of parameterizing zirconium in a different reference, we have here the radial function distribution. So the dark line is our MD simulations. The open circles are the results from experimental data, and the crosses here are simulation for ab initio molecular dynamics. As we can see, our BCC potential matches very well with the experimental data. We also compare with the potential that was already on literature in HCP, and we can see it's not in good, well, it's better, it's not as good as BCC for the experimental data. However, it matches very well a process which is ab initio molecular dynamics. And this is important because we can see that by using molecular dynamics, which is less demanding for computational resources, we are able to reproduce the ab initio data. So now, as I mentioned before, here's an example of validation of the potential. So for the aluminum, copper, zirconium, we have different comparison of enthalpy of mixing. The colors are experimental data. As you can see here, the less accurate is the aluminum copper. However, since we are working on low concentration of copper, we are deciding whether if we keep this potential or we're going to keep the parameterization so that the open circles, which are MD, can better match the overall enthalpy of mixing. So as I mentioned before, we already started simulation for the binary aluminum zirconium. So I'm showing here in green the solidification of the FCC matrix. And in the other figure in yellow, we are presenting the atoms that are oriented in an icosahedral structure. So as you can see, as the FCC matrix grows, uh, there's less atoms in the icosahedral structure, and the remaining ones are only in the grain boundaries. So this is why we study the icosahedral, because it's an indicator when solidification starts and when it ends. So here in the graph, in the plot, I'm presenting different concentration of zirconiums into the aluminum. Let's take the first example where we only have 1%, which is the orange line. We start with a mixing at 2000 Kelvin. We start with a cooling, and then we can see that the maximum is when solidification starts. It's the maximum of the icosahedral fraction, and then it starts to low down, and by the end, we can see the end of crystallization in here. So as we can see, as we increase the amount of zirconium, the amount of the icosahedral structure increases as well, and even in the melts. So in here, we have the glass transition, which means that after the concentration of 5%, we were not able to have a crystal structure, but instead a glass structure. So we were also able to perform some simulations for intermetallics. So here I'm presenting the example of aluminum 3 zirconium. So we take from literature an image of this intermetallic. We then export it into MD. I first created an L12 fashion structure, then it was heated, and then we perform a relaxation. As you can see from the heating, there's already a segregation of aluminum atoms in the core of, in the shell, sorry, of this structure. And this is important because it can confirm why those intermetallics can coexist with a liquid with low concentration of zirconium. So as you can see here in the plot of temperature versus simulation step, I made a quenching from 2000 to 400 Kelvin. So the important part here to look at is the blue line, which represents the icosahedral fraction. As you can see, it's really low at the beginning when we are at 2000 Kelvin. However, when we do the quenching, there's an increase of this icosahedral fraction as well, and then it kind of remains during the relaxation. So we also wanted to explore the effect of putting together a L12 structure with a pure liquid. So we noticed at 900% that this L12 serve as a reference for solidification of the FCC aluminum matrix. So in green, we can see the FCC matrix, how it grows when it's put in contact with the L12 structure. And the same happens when we have the same simulation but at 500 Kelvin. So now for my future work, now we're aiming to study also the aluminum, zirconium, and titanium. So from literature, I started to look at it, and there's already, we can see that the small amounts of titanium or zirconium had an effect on the aluminum alloys. So now we're intended to study this part by not only by molecular dynamics, but also experimentally. So in this way, we can have a more complete work that will consist on classical thermodynamics, experimental, and MD simulations. So as I mentioned before, we are using the mean seconds near neighbor formalism because it allows us to have a homogeneous database to account for the binary interactions. So from the previous work, aluminum zirconium is already parameterized. And the advantage here is that we found on literature the parameterization of aluminum titanium. So this is what we're going to use to complete our database. So to finish this work, at least for MD, we are working on the parameterization of titanium zirconium. So once this parameterization of the binary is going to be completed, we will have automatically the ternary system. So overall, I presented a little bit the stability of the icosahedral or short-range ordering for aluminum chromium system. I also presented a little bit about the gas forming ability in the binary aluminum zirconium and some of the challenges we're facing for the aluminum copper parameterization. I also presented some simulation regarding the intermetallic aluminum 3 zirconium. At the end, as I mentioned before, for our further work, we're only aiming to finish the parameterization of zirconium titanium so we can have our second ternary ready for simulations. So thank you, and I'll be here if you have some questions.
Thank you, Ricardo, for this presentation. It was really clear. So we're right on time, so I'm pretty pleased that we practiced a little, so we